Good afternoon. I'm sorry that I can't be with you today. I have jury duty, so I've recorded this in advance. Um, if everything goes really well, I might be back before the end of class if I don't get selected to be on a jury, which is my hope. Anyway, today we're just finishing up a couple of leftover things from sections 2.1 and 2.2, specifically the Sandwich Theorem, which says that if g of x is less than or equal to f of x, which is less than or equal to h of x, for all x not equal to c, again with limits we don't care what happens at the particular c value, in an interval about c, and the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x is equal to L, then, because it's sandwiched in between those two, the limit as x approaches c of f of x is equal to L. I think a diagram for this is probably in order. So let's draw what this might look like. So we're going to need a x value c that we're going towards, and a y value L. And I'm going to put a hole there just so I have something to aim at. So g of x is the lower function, and it really doesn't matter what it looks like, but I do know that it has to go to L as x goes to c. So I'm going to start there, that way I won't miss it. Doesn't really matter what it looks like. And over here I'm going to go like that. It really doesn't matter what it looks like. Then h of x has to be above that. And just to make it simple, I'll draw something that looks kind of like a squiggly parabola. I guess I should probably label those. So this is h of x, and this was g of x. And f of x is always in between those for some interval around c. I'm going to make it always be true. I'm going to go, so it's got to be in between those two. This is why it's called the Sandwich Theorem. A sandwich is two pieces of bread with something, generally meat, sometimes cheese, cheese, stuck in between them. So this is our function f of x. If the lower function and the upper function both approach L as x approaches c, then because this function is sandwiched in between them, it must do the same thing. Now, how does that work out? Well, let's do a couple of examples. For the first one, we want to show that the limit as x approaches 0 of x squared times sine of 1 over x is equal to 0. And you're like, okay, what am I supposed to do here? Well, the key is to realize that sine of anything has limitations. It only has values between -1 and +1. So what we can do, we have to set up the sandwich part. We're going to go, okay, this at the very least is going to be -1. So I'm going to say that x squared times -1 is always going to be less than or equal to x squared times sine of 1 over x. And because the largest value that sine of anything can be is +1, I'm going to say that's going to be less than, in turn, x squared times 1. So your first step here is to set up your function as the inner part of the sandwich. Then we need to find, well, what happens as x goes to, in this case, 0, but it could be anything, to this farthest left function and this farthest right function. So the limit as x approaches 0 of x squared times negative 1, well, as that gets close to 0, square it, that's going to be really, really close to 0, times negative 1, it just kind of laughs it off and goes, yeah, that's going to 0. And on the other end, the limit as x goes to 0 of x squared times 1 is also equal to 0. So we can say, therefore, the limit as x approaches 0 of the middle part, our function that we're interested in, x squared times sine of 1 over x, also goes to 0. This illustrates a point that is going to come up throughout the year. When we're applying a theorem, frequently we don't bother to say the name of the theorem. What we do, though, is show that we have fulfilled the hypotheses, in this case, that g of x is less than or equal to f of x is less than or equal to h of x for all x in some interval, and I just said it was true always. And the limit as x approaches, this left function approaches some value, and the right function approaches the same value. Then I make my conclusion true. So you don't have to say that you're using the sandwich theorem as long as you lay out the hypotheses as they apply to this particular problem. The sandwich theorem also applies for limits as x approaches either positive or negative infinity. All right, so let's find the limit as x approaches infinity of sine of x over x. Well, again, and you may be going, you're cheating, you're using sine of x again. Well, this is why we do it, because it makes things like this a lot easier. So I know that sine of x is at most 1 and at least negative 1. So I'm going to replace the sine of x with negative 1. Negative 1 over x is going to be less than or equal to sine of x over x, which in turn is less than or equal to, well, because the most sine can be would be 1 over x. So let's take a look then at the limits. The limit as x approaches infinity of negative 1 over x is 0. Likewise, the limit as x approaches infinity of 1 over x is also 0. Therefore, the limit as x approaches infinity of sine of x over x must go to 0 because it's sandwiched in between those two. And just for kicks, let's take a look at what that graph would look like. That isn't it. So clear all these things out. And always make sure that your calculator is in radian mode. Unlike physics, we will pretty much never use degrees in this class. So I had negative 1 over x as one side. The other was positive 1 over x. And let's do a zoom standard and see what those look like. You're like, okay. We're interested in what happens out here towards infinity. So I don't really care what happens at 0 because we're doing as x approaches infinity. So what I'm going to do is I'm going to make this a little different in the window. Let's go from, say, 5 to 100. Yeah, let's go 10 to 100 and let's count by tens. That's going to be really, really small. So I'm going to make my minimum negative 0.2 and make my maximum positive 0.2, and I'm going to go by 0.1. Let's see what that graph looks like. Oh, yeah. You can see that as my x values get larger, this appears to be approaching a y value of 0. Now let's look at sine of x over x. Hopefully it'll be sandwiched in between those two. Sine of x divided by x. And there it is. Happily oscillating back and forth, but constrained by those other two. It is sandwiched in between. So if we wanted to see it going to 0, well, we could get silly with it and make this go to 1,000, which really isn't all that big a number. And let's count by hundreds. And what happened there was it got so close to the axis that you can't see it anymore. All three of those graphs are so close to the x-axis that you can't distinguish them from the x-axis anymore. All right, well, I hope that you guys have a great day. Your assignment is posted in RenWeb and on Google Classroom as normal, and hopefully I will see you on Friday.